In this video I will tell a little bit more about all the clustering methods that you've seen in the course so far. So to be clear, I'm going to talk about hierarchical clustering, the linkage and distance measures that you've seen, centroid clustering, where you do have to define how many clusters you think you will find, which can be used by k-means, k-medioids and k-modes. And then I'm going to tell you a little bit more about how to find the optimal number of clusters in centroid clustering. And finally, I'm going to say a little bit more about the differences between the centroid and density-based clustering. Now, with hierarchical cluster methods, you can either do it bottom-up or top-down. Now, I think the best way to view this is when you look at Google Maps, for instance, and you zoom in. So that means it's a divisive cluster method, right? So you go from very far and you take every time you zoom in a little bit. So in the beginning, all seems just one thing, one point on the map, for instance, the Netherlands. But then if you zoom in, you see like the different provinces. If you zoom in further, you see the different cities. If you zoom in further, you see the different streets. So that would be a divisive clustering technique, where you start from all the data points in one cluster and then just zoom in and divide them in different clusters every step you move down. Now the agglomerative is the other way around. So there you start with all the data points in one cluster and then every step you merge them based on the distance matrix until they all are merged in one cluster. Now if you do this, you can create a dendrogram, and this will actually tell you how many clusters are ideal. And so when you look at the bottom line, there you see that all the observations are clustered in their own cluster. Now you see that some are clustered together very quickly, right? So these are actually the first observations that are clustered in one cluster. So they are very close together, they have a very low distance. And then the next step, there's going to be a few other clusters that are formed. So it seems that these observations are clustered, these observations are clustered, and then another step, you see that these former clusters are now merged together into one cluster, and here the same happens. So when you do this like in consecutive steps, at some point, many clusters will be formed. And when you look at these lines that are vertical, that actually show you how long it takes for some clusters to be formed. So you can see that this group of observations is different from this group of observations, because it takes a long time before it is clustered together with the others. Now, so these vertical lines can then show you how many clusters might be useful to look at. So we see that these two lines are very long, right? So before everything is clustered together, it takes a long time. So 2 clusters is definitely useful. Then we see that these lines are also pretty long. So that means that 3 clusters can also be very useful, right? So we count vertical lines, 1, 2, 3 clusters at this height. Then these clusters could also be meaningful, saying like you have 1, 2, 3, 4 clusters. Now whether you draw the line here and say there's 4 clusters, or whether you draw the line here when there's 3 clusters, that's really up to you. So there's no specific test that can tell you this is the optimal number of clusters. You really have to look at your solutions, maybe inspect the 3 cluster solution, inspect the 4 cluster solution, and look at whether it makes sense. Okay, so the linkage methods, those are the ones how you connect the clusters together. So you could do this within a cluster. There are several observations, right? So here we have like the simple case where you have 2 clusters, each having 2 observations. Now, then you can calculate the distance just on the cases that are closest together, which is the single linkage. You can also do it on the cases that lie further apart, right? So they are most different with respect to the variables. So that's the complete distance linkage. Now you can also use the average linkage, which means you're going to take into account all the points in the data set. Now depending on this linkage, of course, you get like different clusters. So it is important to choose the linkage according to what you think is useful. So you can imagine the minimum linkage actually, emphasize the similarity between the clusters because they take the points that are most similar. The complete linkage actually emphasizes the spread of the cluster, because if you have like two cases that are very far apart but still clustered together, then a complete linkage will actually accentuate this distance within one cluster, right? So if this point would be here and this would still be one cluster, then this distance now is much further, it's much larger. Now the average linkage tries to solve this and takes into account all the points. Now, how do we calculate these distances? Now, very often they use Euclidean distance. Now, this is the formula for Euclidean distance. So as you can see, now what does it mean to use Euclidean distance? So as you can see, there are many different variables. So this x is a value for variable 1 for object A, and this x is a value for the variable 1 for object B. Now you see I subtract 2, right, because I want to see how they differ with respect to that variable, these two objects, and I square it to make sure that negative values are now also positive. And then I sum it with the differences on all the other variables. So this is for the second variable, and this should continue until the nth variable. Now if you sum all of these differences together, then you can square root this large number, and that will become the distance between the objects A and B. Now usually, of course, you don't have two objects, but you have many objects, so you do this for any kind of combination of objects, which gives you a matrix. Now, I think a disadvantage of the Euclidean distance is that you have to sum all these values for all the variables. So that means the more variables you add, the larger the distance it becomes. So that's called the curse of dimensionality. The more variables you add, the different it will lose its meaning because the distance will become larger no matter what. Yeah, so it doesn't matter whether they are similar on this last variable, it will still become larger. Now, here's an example where we have not done it for 2 objects, but actually for 6 objects. So as you can see, we calculated the distance for all 6 objects, and you see that these points, these are now distances between B and A. This is the distance between A and F, and for each point we can then say, how far are they apart based on these 2 variables, because we only included 2 variables, x1 and x2. Now the D and F, you see that there's a very small distance between each other. And this is clear because they score the same on one variable, and on the other variable they're very close together. It's only half a point apart. So this means that you square the half point and then you take the square root, which lands you the 0.5. Yeah? Now, as you can see, these two are now clustered together. Now, in this approach, we cluster these two together, and then we calculate the new distances based on this new cluster. Yeah, so we can either take the single linkage, the complete linkage, or the average linkage, but we treat D and F as one case in this next step. Now we continue until we have clustered most of the cases. So here I clustered A and B together, and I cluster D, F and E together. So now I only have the distances between A and B and C, A and B and D, F and E, and C, D, F and E. Yeah, so now it's a very small matrix, and this actually gives you like one of the final steps where I say C should be clustered together with D, F and E, and then we have to recalculate this again, and then we'll see, you know, which ones will be merged together. Now if we plot this in a dendrogram, it will look like this. So it means that D and F is clustered first together, we saw that. Then A and B is clustered. Then D, F and C is clustered. And then this cluster will be merged together with A and B. Now, there are other distances, there's many different distances. In this course we only treat the Euclidean, the cosine and the Manhattan. So the cosine distance is measured as such. So this is the formula to measure this. So it means we have a matrix of the variables and we multiply it. So this is actually the sign for a matrix multiplication. So we multiply the transformed matrix with the original matrix, yeah, as we can see here. So A and B is actually the same matrix, but here we transform A, we multiply it by B, and then we square B in order to get this part of the formula. We calculate the sum of the columns, which is done, the summation marks means that we're going to sum it across the I, which is the columns in this case. So we sum it, then we square root, we multiply it by the matrix that is done on the original matrix. So here we do it for B, we have the call sums, and then we say, okay, you know, since this one, so A is the same as B, just transformed, so then we just transform the outcome of this. We do the matrix multiplication between these two sets, and we take the square root. Now that's going to be the denominator, and then we have the numerator and the denominator, and that's actually our distance matrix for the cosine distances. Now you can also let R do this. That's actually a package that actually calculates this. Make sure, and this also holds for this formula, is that when you input the data, you transpose the data frame. So the data frame has variables, so this part of the formula takes from the data frame a set of columns with certain variable names. These names are saved in vars, which is just a character vector, and the T stands for that we tilt it on its head. So now the vars are like the rows, and the variable, the observations, are the columns. This is necessary in order to make the distances about the observations and not about the variables. Yeah. Okay, what is the difference between the cosine and the Euclidean distance? Well, for the Euclidean distance, so you know, you could view these distances as a way of like drawing a vector into a space, right? So here we have x1, x2, well, actually this x1 and this x2, meaning that the vector actually shows how these data points, so these observations A and B, how they are scoring on x1 and x2, right? So here we see that indeed B scores relatively high on x2 and relatively low on, well, they call it I1. Yes, same holds for for A, so actually it scores pretty low on x1 but very high on I1. So if you draw a line, that creates a vector, right? So these lines can also be expressed in numbers. So what you see when you calculate the distance between A and B, with the Euclidean distances, you take the final points and you calculate the distance between them. So that means that it becomes very large number. For the cosine distances, it uses these lines and it just calculates the angle between the two lines. So that means it doesn't matter how long these lines will become, depending on, you know, how wide these axes are. So if a variable runs from 0 till 1000 or from 0 till 1, that shouldn't matter for the cosine distance, because it just calculates the angle. Yeah, so that's why the Euclidean distance is very sensitive to the scale of the variables, but the cosine distance not so much. Now, so far we have seen how we can do clustering for numeric variables where we can just have numbers, but there's also a lot of categorical variables where you cannot really use the numbers. Now, here's an example, an intuitive example of how you can picture this. So there's two observations here, both at the endpoints of this map. The green line shows the Euclidean distance. So there you just calculate the average, and then actually you can just draw the line directly. With the Manhattan distance, you don't do this. You just say, okay, how do I get from this point to that point? It could be like this, it could be like this, it could also be like this, right? So there's many different ways to get from one point to the other. That's why it's called the taxi driver distance. But these lines, these other lines, they are determined in the number of steps you need to take, right? So the number of blocks you need to run, right? So these are all blocks. And here as well, there's all blocks that you need to run. So that's the Manhattan distance. The Manhattan distance basically can be calculated by this formula. So this only works for dummy variables because they are numeric, they are only differing 1 point. So it means that the a minus b is always a 1 or 0. You take the absolute difference, so that means that the negative values are excluded, but you don't square them. You just remove the negative sign. Then you sum it for all the variables, and then you take the square root. Well, in this case, you know, m is 1, so this doesn't do anything. And you take the sum of these differences between the 2 points. So this is the Manhattan distance. Now, if we also rewrite this formula to make it like Euclidean distance, we would remove the square bracket, the straight lines, and replace it with round brackets. So we don't take the absolute differences, but we take the relative differences. M is now no longer 1, but it's 2. Yeah, so we square them here, and here we take the square root. So you see that they are very similar. But the difference is that for the Manhattan distance, you sum the absolute differences, which are only relevant for like dummy variables, and for the other, it will be the relative distances. Okay, let's talk about the centroid clustering. So how does it differ from the hierarchical clustering that we saw before? Well, with hierarchical clustering, you don't take any decision on the number of clusters, you just run the analysis and you look at the dendrogram. Now, the problems is when there's like lots of error and when the initial decision is more influential. With the non-hierarchical clustering, the advantage is that it is faster, but you need to specify the number of clusters and you need to set the initial seeds, because that's kind of like determining how it starts and also the solution. Now, one of the most used centroid clustering techniques is k-means. So in k-means, you need to specify the number of clusters beforehand, and it randomly assigns each observation to a cluster. So it calculates the centroid of each cluster, and then it looks at the distance between all the objects to the centroids, then see, okay, you know, is this really a good way to define the centroid? A group again on the minimum distance, then we'll say, okay, you know, maybe some objects need to be removed and they have to be moved to another cluster. And then they start again calculating the centroids, calculate the distance of all the objects to the centroids, see if some clusters or some objects should be moved to other clusters. Now, and this last part is done on minimum distance. So for each cluster, you actually calculate the within sum squared. Yeah, so that actually shows you how the variability is of all the objects within one cluster. Now, how does it look? it is an iterative process, as we have seen before. So first it just points to means. In this case, this is k-means, so it just points to two means based on the starting values. And then based on these starting values, it starts to iterate, right? It starts to calculate, okay, how much variance is there within this cluster and how much variance is there within this cluster. So then it moves the mean a little bit towards another spot where the variance within the cluster is reduced. And so you also see that more points are now assigned to this cluster to make them, because by assigning these points to this cluster, you reduce the within sum squared in this cluster to such extent that it becomes better overall. Now the same happens here, so even more points are assigned to this cluster, and then this mean is now moving much more towards that side. Same goes here, and in the end you will find two clusters, one that is of these points and one that consists of these points. So apparently the solution reduces the total within sum squared. Now it is a greedy search, so the same also holds for the partitioning around the medioids, right, where we do not take the means but we take the medioids. So again, you select a few data points as medioids. And remember, means might not appear in your data, but medioids and modes are actual points in your data. So medioids means medioid is the central point by which 50% of your data set is below it and the other 50% above it. So you relate each point to the closest medioid, you improve the fit, so you decrease the within sum squared by swapping 2 points, right? So you say, okay, I take just 1 point random for each medioid. You just swap it with another point in that cluster to see if you can reduce the within sum squared with this new medioid. Yeah, so if it is reducing, then you remember it, and then you do it again. Now, it can be calculated on numeric variables, but also on categorical variables, because the medioid, like I said, is the middle observation. So you can also do this with like categorical variables with many levels. So with countries, there's always one country that is more often mentioned than other countries. For instance, if you ask someone where they go on holiday. Now, how do you do this in R? You use the PAM command. So here we include the distance matrix based on Euclidean and one time based on Manhattan. We say we want to retrieve two clusters. You use the PAM function, and we plot it by the class plot. Now the k-moid clustering is the most frequently using value. So there you also choose like an initial cluster membership. You update them according to these memberships, and then you estimate it using the updated cluster modes. Yeah. Now, the advantage of k-modes is that it's non-parametric. It's the same holds for k-medioids. It deals with categorical data, and it's as fast as k-mean, so it can handle large data sets. Now, how do you find this optimal number of clusters? You can do this by trial and error. Just try out a few number of clusters and try to interpret the results. Now, this can be very cumbersome. It can take a long time, and there's no clear criterion. So some general rules are to avoid empty clusters. So whenever you have a solution, look at the number of cases that are assigned to that cluster. If you have clusters that are very small, it might be that these are outliers and or they're just not very interesting. So most of the time for clustering, people are looking for like just a number of set of groups. Usually 50 groups are not very informative. So very often people look at the cluster solution from, let's say 2 clusters till 10 clusters. And after 10 clusters, it becomes cumbersome to interpret. Okay. Avoid clusters that are very alike in the terms of variables. So look at the means on the variables for each cluster. Yeah, and like I said, too many clusters complicates the interpretation. Now, it's better, you know, to use like these methods because they actually have like a way to get to the best solution for each number of clusters. So the elbow method, the silhouette score, and the gap statistics, they all show you how well the cluster solution from 2 or actually 1 cluster till 10 fits. The within sum squares takes the differences between the objects and the cluster mean within each cluster and sums it across the cluster. So you get like a total within sum squares of all the clusters combined. Now, as you can see with one cluster, this is very large because that's basically all the variance in the data. Then if you cluster it into 2, the within sum squares actually reduce. So because you form 2 clusters, the variance within the cluster is smaller. That is also the case for 3 clusters and for 4 clusters, but then when you create 5 clusters, something strange happens. The variance actually increases. So this cluster is not very useful, but then if you go down again, add another cluster, it actually reduces again. Now, after a certain point, the reduction is very small. This is called the bend in the line. So this within this elbow method, it means that at the elbow, like where it really has this nick, the knee, there you might find your optimal clusters. Now in this case you can find 2 situations, maybe 4 clusters actually has a good solution, but 6 clusters might also be informative. So I would then further inspect the 4 and the 6 cluster solution. Another method is the silhouette method, where you calculate the silhouette coefficient for each observation, but also for within each cluster. Now then you average across all the data set, so you get like the average silhouette width. Now the silhouette scores, they actually show how similar they are in size. So it would be nice that you have high silhouette scores and that the silhouette scores per cluster are very similar. Yeah, so therefore it draws like this dotted line to indicate that this is the optimal solution with the highest average silhouette score. Now how does this look? So this is a silhouette plot where we actually say, you know, for each observation within each cluster we calculate the silhouette score. Now you see there's some negative score, so this observation does not fit very well with this cluster. And we also see that, you know, the clusters, they vary in the silhouette scores. So very often when it varies a lot, it's not such a good cluster, but this is also a big cluster, so it's likely that it will differ. Yeah, some points will be more similar and some points will be very dissimilar. Now, you would like to have clusters that are very similar in size, because that's very strong, high density clusters. Now the gap method actually runs the multiple runs with different number of clusters, same as before, and it calculates the intra-cluster sum of squares by the gap statistics. The higher it gets, the better the solution. As you can see here, the 8 is considered the best optimal solution. Now finally we will discuss the hard versus soft clustering, and in this course I only go over the DBscan. So hard clustering is called when you have like one object or one point to be the centroid of the cluster. Yeah, so this is actually really true, you know, in the k-means, k-medioids and the k-modes. Yeah, so you assign each observation to a certain cluster. Now the soft clustering, that's where you don't really have like one data point, but it means that you just have a probability that it will be assigned to a data point. Yeah, so it does not need that one data point is only assigned to one cluster. There's a probability that it will be assigned to one cluster and a probability to be assigned to another cluster. Now the centroid base, this is like a graphical depiction of this. You have 2 points and you just calculate the distance of all the points with that point. Now with the distribution base, you calculate not like one point to address like the centroid of the cluster, but you group these objects together based on how close they lie together. So either it's based on the distribution or the density. So as you can see, when it is round, it means there's a normal distribution. So there's a center, and then there's like, you know, the points, like the further you go, move away from the center, the fewer points there are in each direction. Now, the good thing about the distribution base with DBscan, it actually allows you to have like distributions that might not be like normally distributed. So you see that this ellipse, it actually says, okay, you know, there is a centroid, but the points only move into two directions, it seems. Now with the density base, you're also able to pick up like patterns like this, where you have like a decision boundary that is not straight but actually round. And so these distribution and density based cluster techniques, they are able to pick up many different sizes and clusters and forms of clusters. Now, how does it work? It actually has two parameters, the epsilon, which defines the neighborhood, and the min PTS, which defines how many points there are. So the epsilon defines like how wide these circles are, and the min PTS, how many dots there are within the circle. Yeah, and these two parameters together define how many clusters you will find. Now, you don't have to specify how many clusters there are beforehand. It can find many different shaped clusters. It has a notion of noise, so it is robust to outliers, right? Because you see that here, for instance, there's a dot that does not belong to any cluster based on the min PTS and the epsilon, and hence it's indicated as noise. Yeah, it only requires two parameters. Now the disadvantages is that, you know, some points might be, you know, belonging to two clusters, and maybe one cluster is more likely depending on the order of the data. The quality depends on the distance measure, so the epsilon, the Euclidean distance. It cannot cluster data well with very large differences in densities. And if you don't really understand the data and the scale, it might be very difficult to find like an epsilon that has a meaning. Okay, so this was, now we reached the end of this recap. If you have any questions, just let me know.